So I just want to, we've been sort of equation heavy for the last few lectures, right? Lots of just, well, the linear algebra stuff is sort of pure math, and then lots of derivations and other things. So let's back up and provide a little context and, or, recall where we're going with all this. So, this is reservoir geomechanics. So we want to solve problems dealing with a reservoir in which mechanics plays a role. And we've talked about some of those on the first day, like wellbore stability. And wellbore stability has to do with the failure of the rock. Well, rocks fail when the stress in the earth exceeds the strength of the rock, right? And very soon we're going to learn about some failure models that determine, now that we know a little bit about stress, we can actually use failure models to determine if and when the rock will fail, and then we can apply that to wellbore problems and make a determination if the wellbore is going to be stable, which can then lead us to make better decisions about wellbore control, designing casing strings and other things like that. Or simply, a lot of times now we're drilling horizontal wells, and the orientation of the well can make a big difference in whether the wellbore will be stable or not, okay? So that's one application. Of course, if we're doing some type of water flooding operations or flooding operations, we're injecting fluid into the reservoir, which is going to increase the pressures in the reservoir, and those can exceed, if there's faults in the regions, those can exceed basically the normal stresses on those faults and cause them to slip, okay, and produce seismic activity, which can be undesirable, right? And other things like depletion. Depletion, in fact, in some regimes can help production, and so depletion has to do with stress changes due to production, and that can actually increase production for some time due to things like compaction drive and other things. And all these things we'll cover, but I'm just trying to, we've been looking at a lot of equations, so let's just back up a second and know why we're doing it. So, okay. So now we know a little bit about stress, at least mathematically, right? We defined it mathematically, and we talked about the eigenvalue problem to determine what the principal stresses are. And then today we're going to talk about why that's sort of important, because it turns out that the easiest way to characterize the stress in the earth is via the principal stresses. And remember that stress is dependent upon the coordinate frame, right? So the easiest way to characterize the stress in the earth is via the principal stresses and their relation to some geologic coordinate frame, typically just your cardinal directions of the earth, north, south, east, west, right, from the surface of the earth. That's the easiest way to characterize the stress in the earth. Of course, that's not the stress in a wellbore, because a wellbore could be arbitrarily oriented, right? And so we'll need to learn how to take the stresses that we characterize in the earth via the principal directions and their relationships to the cardinal axes and transform them into wellbore coordinate systems so that we can make a determination if the wellbore will be stable. Or likewise, transform the stress onto the plane of a fault so that we can determine if the fault's going to slip or not. Okay? So that's sort of where we're going here. So principal stresses and directions in the earth, right? So we learned about principal stresses and directions mathematically. Let's talk about them from a more practical standpoint of where in the earth. So what I'm going to do is I'm going to cut out a very large piece of the earth that we'll call a half space, right? So this is sort of like a little, well, not little, but a large section of the earth that we can consider to be semi-infinite. We're going to place a coordinate system right on the surface of the earth such that one direction is straight down, normal to the earth, passing through the center of the earth, and then the other two coordinate directions would be in the plane of the earth, right? So something like that. Okay? So we're gonna take that now, we're gonna cut it out of the earth. and plop it down there, and we're going to write down our equilibrium equations, which we had derived earlier. Okay, so these are equilibrium equations, or conservation of linear momentum, and let's look at how it applies to this half space that we cut out of the Earth, this very large half space. So the first thing we're going to do, the terms on the left-hand side are accelerations. Okay, so in problems in reservoir geomechanics, we typically don't concern ourselves with acceleration because the motion is slow. It's tectonic motion. Okay, the motion of the Earth is slow. Right. Now that's not, of course, true if you're dealing with earthquakes. Right. If you're dealing with earthquakes very near the focal point of the earthquake, you'd very much be concerned about the acceleration of the Earth. But here we're going to, for the most part, say that because the tectonic motion is very, very slow, those terms on the right-hand side are going to be negligible. Right? So now we're really dealing with a statics problem, an equilibrium problem. Right? So these are all equal to 0. Now, remember our half space, and it's sort of the reason I made the point to cut it out of that picture of the Earth. Our half space, the surface there, the gray shaded area, is in contact with a fluid. Over the entire surface of the Earth, it's in contact with a fluid, right? What are they? What fluids is it? What fluid is it in contact with? The atmosphere, so air, right? And there's another one, and water. Right? Everywhere on the Earth's surface, that gray shaded area is in contact with a fluid. Can fluids impose shear stresses? No. Ideal fluids don't impose shear stresses, right? I mean, for the most part, that statement is not completely true if you had like viscoelastic fluids or something else. Air and water, as an engineering assumption, do not impose shear stresses, right? They don't have any. Again, as an engineering assumption in the context of geomechanics, understand that, due to boundary layer effects, if you're in an area where the wind is blowing 100 miles an hour, there would be some small shear stress on the Earth, but it's some small shear stress in that boundary layer region, but that stress is insignificant compared. It's not going to cause the plates to move, right? It's not going to cause tectonic motion. Okay, so those stresses are negligible, and of course, due to equilibrium, if I have a fluid that has no shear stress in contact with a surface, then there's also no shear stress on that surface, right? It's a statics problem, okay? So if you remember we had, if I were to say, cut my little idealized cube, cut it out such that the top of this cube was also in line with the top of the gray shaded area, the top of my half space. And then we draw the components of stress, right? Remember, so we had like sigma 3.3, sigma 3.1, sigma 3.2, right? And those signs, those arrows may point in different directions than what I had originally drawn them, but that's just a sign convention, right? In geomechanics, we typically use a sign convention that compression is positive, and that's due to the nature that essentially over a few feet down into the Earth, all the stresses are always in compression. And there's two reasons for that. Essentially that most rocks are very, very brittle in tension. So if there was any tension, you'd just fail the rock. Right? And the other reason is below the water table, all the way down to the ductile brittle transition, so from a few hundred, a few tens of feet, all the way down to 20 kilometers, there's fluid in the Earth. It's saturated with water, hydrocarbons, and that fluid has a pressure itself due to just the hydrostatic head, the gravity has a pressure. And so there has to be a compressive stress that's at least greater than that pore pressure. Otherwise, you'd hydraulically fracture the earth. So those two things give evidence to the fact that the stress on the earth is always in compression, and we don't want to carry around negative signs everywhere. So we make the sign convention that stress in geomechanics is positive. This is actually quite different in any other field of mechanics. Probably when you took engineering mechanics, it was the opposite, right? Stress is positive in tension. Okay, but in geomechanics, we typically talk about stress being positive in compression. And so that's the way I've drawn my little stresses there, okay? So we've already determined because the gray shaded area is in contact with a fluid, and fluids don't impose shear stresses, then the shear stresses on the surface there must be zero, okay? So sigma 3.2 and sigma 3.1 must be zero, okay? And of course, due to angular momentum, we decided in a previous lecture that sigma 3.1 is the same thing as sigma 1.3. And sigma 3.2 is the same thing as sigma 2.3. So all of those terms disappear. Okay? Now, our principal stresses must be orthogonal, right? They make a right-handed coordinate system, right? So there's no possible way to draw a right-handed coordinate system in any way. Yeah? Not necessarily. Not necessarily. Yeah. Not necessarily. Because, I mean, you could, it is conceivable that you could, so 1, 2 would be like, what's my positive one direction? That way. So 1, 2 would be like that, right? So it is possible that you could have. Yeah. So anyway, but all the point here is all the terms with a 3 in them are gone, except for this one. Okay? Now I can't draw an orthogonal coordinate system in any way that doesn't have some component in the 3 direction, right? So I know my principal stresses are orthogonal, so I'm looking for a way to draw an orthogonal coordinate system somehow that doesn't have a component in the 3 direction, and it's impossible, right? It has to have a component in the 3 direction. And the only possible one left is S33. So S33 is a principal stress. Okay, it is a principal stress. As we'll see later, we'll see an equation. I'll just go ahead and point it out. Also notice that this last equation reads is equal to rho. I'm going to say B3, okay, but B3, B3 is a body force in this direction, body force into the earth. What is that? It's gravity, right? It's gravity. So, we would have this guy, right? And so then, I can multiply both sides by, partial x3, and then integrate. So I have the integral something like that. Well, that gives me an equation, right? So then this is S33 plus a constant. Right? So this gives me an equation to determine what S3 is. We'll see this in a second. But the point here is just to know that S33 is a principal stress. And typically we denote that as SV, right? So this is the vertical stress. So the vertical stress is one of the principal stresses, which, because we know it's vertical, we also know a direction. Okay? So now we know one of the principal directions is into the earth, always. Okay? And remember, I drew this coordinate system at the surface of the earth. So this is absolutely true at the surface of the earth, because the way we got here was we were talking about the surface of the earth where there's no shear stresses in the 3 direction, right? 3, 1, 3, 2. But it turns out that this actually holds all the way down to the ductile brittle transition. And we know that due to earthquake focal data and other things, right? So while it's absolutely true at the surface, according to the arguments we made here, it's also true all the way down, say, 20 kilometers, 20, 30 kilometers, okay? That the vertical stress is a direction, okay? Is a principal direction. Well, and the principal directions are orthogonal, right? So we know that the other two are in this plane, right? We don't know their direction, but we know they're in the plane, right? So one of them's down, the other two are in the plane of the surface of the earth. Right? So we need 4 things to completely describe the state of stress on the earth. The vertical stress magnitude, because that's one of the principal stresses. And that one's actually pretty easy to either estimate, and we'll learn some rules of thumb for its estimation in a second. We can either estimate it, or we can measure it via density logs, essentially, through the integration of density logs in that equation that I just sort of derived. Right? So that's one's actually pretty easy to get. We can always estimate it relatively well, and we can measure it via density logs from a wellbore quite well. Okay. SH max is so it's one of the other principal directions, principal stresses rather. It's one of the other ones, and we denote it as there in the book. By the way, I guess I should mention, essentially today we're finishing chapter 1 of the book. So if you want to read along to provide some background and context, we're finishing chapter 1 in the book. My notes try to use the same notation where it makes sense as the book. So he uses capital H for SH max. Okay, so that's the maximum horizontal principal stress. The other one is S little h, right, min, so the minimum horizontal principal stress magnitude. So there's 2 in the horizontal plane, a maximum and minimum value. Those are 3 principal stresses. And then we only need 1 horizontal principal stress direction, right? Because we know the other one, right? We know one of them is down, one of them is in the direction of the vertical stress. So if we can just figure out the other one, we can fully characterize the stress in the earth. And it's typically associated with the direction of SH max, and this has to do with the fact that the way we often measure this is from mini fracs, little hydraulic fractures, okay? And hydraulic fractures typically grow in the direction of SH max, and we'll talk about why that is, okay? So not always, but typically that this last piece of information is associated with SH max, the direction of SH max. And when I say direction, that's with respect to the geographic coordinate system, the cardinal frame, right? So with respect to north, east, west, south. So often we'll be given, we'll be given the principal stresses and the direction of SH max with respect to some cardinal frame. It's to the west or something like that. And then from that we can fully characterize the state of stress. We know everything we need to know.